What's up, bitches? Today we're going to learn free vibrations. So the way mechanical vibrations is set up is the class uses a mass spring damper system, like this, for example. This is something that you should have learned in your past classes, okay? And the way they build the equations for this system here with like the inertia and then the spring force, whatever, all those equations, they use the same principle to build the equations for mechanical vibrations, okay? So what you see on screen are the four most basic equations that I could think of for mechanical vibrations. Omega n is the natural frequency of a system. It's equal to the spring constant k divided by m square root. This is in radians, by the way. This omega over here, this is just the frequency of, it could be anything, I'm just saying the frequency. This is in radians. The way you could have this is you take the frequency in hertz, multiply by 2 pi to get radians. Then you could also take 2 pi divided by the time period in seconds. All right. Omega d is the damped frequency, okay? It's equal to the natural frequency here. And this, I think it's zeta, is the, what's called damper ratio, I think. That's the damper ratio. And this is the damper coefficient. It's equal to this, okay? I don't know if you're going to have this in your formula sheet, but these are things that you have to know by heart. So what the fuck is free vibrations? Free vibrations is basically when you have a system, a mass with spring, damper, whatever. Free vibrations is when you apply a force, usually at time equals 0, and then you do nothing else and you just let the system vibrate or oscillate. That's free vibrations. Otherwise, if you have a system and you're continuously applying a force, then stopping, then applying a force, whatever, that's free vibrations because there's harmonic oscillations and you're forcing the vibrations. Free vibrations is you just apply a force, like for example when you pick a guitar string and you do nothing else and you just let the system vibrate by itself. That's free vibrations. So the logic that this chapter uses is you apply a force at time equals 0 and then you do nothing else for the rest of the whole time, whatever. There's no force, right? So there's an initial displacement and then you're measuring how it's oscillating the system by itself. So because you're ignoring the f after time equals 0, basically the equation is going to be this. This is from your previous modeling classes with the whole free body diagram, whatever. Except this time you're ignoring the f, so it's just equal to 0. This is the general solution of the whole system. Once you solve this with Laplace or what, you don't need to know by heart, but once you solve it with Laplace, whatever, you get the general solution. All right, this over here is your general solution. That's it. This is, if there's one solution that you have to, if there's one equation that you have to know for free vibrations, it's going to be this one, okay? Well, this is, the x is the amplitude in meters of the mass. E is the Euler's number, it's a constant. This is the damping ratio. That's the, what's it called? Natural frequency, time. And A and B, you have to find them by doing the, usually, by doing the derivative of x and using the initial problems. Not the initial problems, fuck, the initial conditions. That's what you do. And this is the damped frequency, okay? This solution is for undamped or underdamped solutions, okay? Undamped is basically when the zeta is equal to 0, and underdamped is when it's less than 1, okay? So let's say you have a guitar string and you just pluck it and do nothing else, then that means there's no damping, right? So this would be equal to 0, so this whole thing would be equal to 1. And then, if that's the case, if there's no damping, omega d just becomes omega n. The damped frequency is just the natural frequency because there's no damping. So it becomes omega n here too. Now let's say there's again your guitar string, but now there's like damping, like you palm mute your guitar and you play the string. It's going to look something more like this. You're going to be damping it, so it's going to look like this. If there's no damping, there's like zeta is equal to 0, it should be looking like this. until infinite. Well, in real life, eventually it dies out. But in this class, you're assuming perfect conditions, so it goes on till infinity like this. If there is damping, it like decreases like this, and therefore you have to consider this part over here. For both cases, you can use this equation perfectly fine. This bottom equation over here, personally, I never used it, but while doing some problems, like I saw the solution using this, and it looked simpler. But to be honest, I never used it, and yeah, I think it was in my formula sheet, but I just never used it. It was kind of useless. Now, there are some other cases where it's critically damped, which means this. Then you would have to use this equation over here. And overdamped is when the zeta is above 1, and then you would use this equation. Now, personally, this was in my formula sheet, but it wasn't in my exams or quizzes or midterms. So it wasn't my homework problems. I don't know if you want to learn it, but these are what these equations are. Okay, some problems, they're going to give you stuff like this, or they're going to give you like an amplitude ratio, x1 and x2. These are your amplitudes, and it's basically showing how it decreases when it's underdamped, when there's like a damping involved. If it's overdamped or critically damped, it's just going to be a straight line, so there's no like frequency. Whenever you see something like this, you have to use this equation over here. This, I think that's delta, it's the logarithmic decrement, some shit like that. It's basically ln of the ratio of these amplitudes. Once you find these, you can use this equation to find the rest of the values, okay? When you substitute the natural frequency and the damped frequency, you should be getting this, and that way you can find the damping ratio. This equation should be in your formula sheet normally. This wasn't in my formula sheet, but it's not that hard to forget, to be honest. But once you see this, you have to use this equation to find the rest. Okay, so if you haven't realized, this is one of the most complex classes in mechanical engineering. There's a bunch of these fuck-ass equations, and like I think there's like 10 fucking equations per chapter. But the ones that you should know are basically these ones that you absolutely have to know by heart. Okay, they're literally in every question. This one, you don't need to know this one. This you should know. You have to use it for undamped and underdamped. This you could know it if you want. These you should know as well. And these two, just be aware of what they are. They should be in your formula sheet, unless if your teacher's a ass. But you should have these in your formula sheet, and you have to know what to use them for. All right. Last thing, when you do this chapter, you're gonna come across kinetic energy and potential energy in a lot of the problems. Okay. Basically, in this case, it's giving you a super complex system with a bunch of springs and dampers, whatever, and it's giving you to like transform a super complicated system with a bunch of springs, whatever, into like a mass, spring, and usually not damper, but just a mass and spring actually, and it's called the effective mass and effective spring constant. And that way you can compare the super complicated system into just this over here. That's usually what it means. So the way you find those is that you have to use these two equations over here, okay? Kinetic energy is equal to 0.5 times mass times velocity squared, okay? If you're a mechanical engineer or just an engineer, at this point in your education, you have to know this by heart, bro. Same thing for the potential energy for springs, right? PE is equal to 0.5 times spring constant times the displacement squared. You have to know these by heart, okay? Basically, in mechanical vibrations, you have to add up all of the rotating parts, all the moving parts basically, and then you factorize out the 1/2 and the velocity squared, and the rest is your effective mass, okay? Same thing with potential energy. You just add up all of the springs, factorize x squared and 0.5, and what you have left is the effective K, all right? Now, usually you're going to see for the T, there's the inertia to J, okay? It's basically because some questions you're going to have both parts that are moving like in translation motion, and you're going to have other parts that are rotating. You still have to consider both, and then you have to convert them to either theta or x. That's pretty much it. All right, so we're gonna do an example problem just to practice and understand better. And just FYI, this was literally my second quiz in my classes. So pay attention, dumbasses. So basically, it's giving us a super complex system with a rocker arm and a valve, and it's asking us to convert it into a simple system like this that describes the whole system. Okay, so whenever that you see K effective, M effective, whatever, the first thing you should think about is energy, potential energy and kinetic energy, right? So let's start with kinetic energy. It's equal to this, J, this, plus the same thing but with masses and X squared. All right, first things first. This shit on the left, they're not giving the mass, not giving anything, and it's asking us to measure at point A anyways, which is over here. So we can't really take any mass, there's no masses, so we could just leave it as is for now. Well, for now. You could just leave it as is. It's not part of the question, basically. Next, the rocker arm. This part over here, it's giving us theta and it gave us J. So, very simple. That's the rocker arm. Rocker arm. Next, it's giving us, it's asking us the valve, right? Over here, MV. It's equals to 1/2 MV. And it's giving us the displacement of the valve as well, XV. So that's it, XV squared. Plus, now, normally it's usually this, because in almost all of your problems, you're using a massless spring. However, in this question, it's specifying us that the spring has a mass, okay? And like, literally in all of your engineering questions, whenever they give you a variable, you have to use it at some point in your equation, right? So when you have a mass spring, you have to be careful because this is actually a trick question. You have to check your formula sheet, and this is a screenshot of my formula sheet. The first thing written is asking you, well, it's telling you equivalent mass due to spring of mass M attached to the mass M over there, big M. Basically, what's that saying is that if you have a mass, right, big M, and then a spring with a mass M, the effective mass of both of these is equal to the mass of the object plus the third of the mass of the spring. That's what it's saying. However, our mass that the spring is attached, it's not the rocker arm, it's the valve. So we already have M. So for the mass of the spring, you have to pick this one over here. All right? Times. Instead of writing MS like we normally would, you have to take the third of it. The reason why you do this is because when you take a spring and then you stretch it out, like here, for example, if it's attached to a mass and you stretch it out, okay? This part over here displaces a lot more than this part over here, okay? That's why you can't just take MS. That, again, same thing, you take XV dot squared because that's the displacement of it. Let me clean this up real quick. All right, so we got our valve and we got our spring. That's all the parts we need to solve this problem, okay? These are the kinetic energies involved in the system. Now, we have XVs and we got J's, so we have to convert it to either X or theta. Now, like literally in all of the problems when I did this, excuse me, the theta, it's like a lot easier converting everything to theta, all right? Because when you look over here, the rocker arm, let me just redraw it, right? It's rotating. So this part over here, it's not just going up and down. I know in the question it shows like a straight down arrow, but it's rotating, so it's more of an arc, okay? And to find the length of the arc, it's just the radius times theta in radians. That's it, all right? So this this rotation that it's moving, that's XV. That's the actual movement of the valve and the springs. So to find that, it's equal to radius times theta, okay? We have the theta, and the radius is given up there, B. That's it. But if we want to find the derivative of this, you just do the derivative of theta, and then B, it's just a constant, so it's just this. That's it, that's all. So we're going to convert all of this to theta. All right, now the last step, whoa. is to literally just factorize out the 1/2 and the theta squared, the theta dot squared, right? So it's equal to 1/2 theta dot squared j plus mv times b squared, right? Plus ms over 3b squared. That's it. All right. Okay, so next it's asking us to find the equivalent system at point A. So what is point A? It's basically this point over here, okay? You want to compare it to a mass effective over here and a spring. Okay, this mass is going up and down, but this is not exactly going just up and down, right? Since this is rotating, it's more of an arc. So same thing, it's equal to the radius times the radiant, okay? So if you look up over here, if my fucking note stops lagging, you can see that the radius is A. So x at point A, it's equal to the radius, which is A, times theta. That's it. Super easy. All right? So if you want to take the kinetic energy at point A, literally it's just algebra. You just have to factorize, not factorize, fuck, solve for theta. X A divided by A. That's it. Super easy. So therefore, the derivative of theta is just a derivative of XA, and A is just a constant. That's it. That's all. So all you have to do is just replace this over here. T is equal to 1/2 times XA dot A squared. And then this shit, EVB squared plus S over 3B squared. We're going to send this to the other side. You get T equals 1/2 XA dot squared times J plus MVB squared plus S over 3B squared divided by A squared. That's it. So this part, remember that the kinetic energy, it's 1/2 mx dot squared, right? This is your x dot squared, that's your half. So your mass effective, it's this. That is your mass, their effective mass. All right, super easy. Now next, to find the K effective, you have to use the potential energy, right? So you use T to find the effective mass. You use the potential energy to find the K effective. All right, this is equal to the sum of all the spring constants, half, times the displacement squared. All right, if we look at our problem, we literally just have one spring. Okay, so that's equal to 1/2 times the Ks of our spring times the displacement. However, we have to convert it to theta. Okay, you got your rocker arm. Again, it's rotating, so it's not just going up and down. Whenever you have an object, bro, that's rotating, whatever is at the end, it's not just going up and down. You have to remember always that it's always going into an arc, more of an arc motion, equal to the radius times the theta, right? Which in this case, it's B times theta. So x squared, that's just B theta squared. That's it. Now, again, same thing for the kinetic energy that like we did. We isolated, we solved for theta to find XA, right? So all you have to do is replace it. But it's easier if you just factorize it first. 1/2 theta squared times KSB squared. All right. And now you replace this with what we found, over here. 1/2 XA over A squared times KSB squared. All right. Factorize it one more time. You get XA squared times KSB squared over A squared. And the general equation for the potential energy is 1/2 K displacement squared. 1/2's right here. The displacement's right here. So the K effective is this one over here. That is your K effective. That's it. Easy peasy. All right, so we're going to do a little example over here just to understand better. I took this from one of my tutorials. It's basically saying that there's a bike and they're comparing it to this mass damper spring system over here. And it's saying that there's this 5 centimeter drop as it's writing, and it's asking the system response. So when they're asking the system response, it's the amplitude that they're talking about. Now, we can't just use the general equation that I said previously, because we're not sure if it's undamped, underdamped, critically damped, or overdamped. So we have to find zeta. That's like one of the first things that you have to do. So they give us, well, this is from my tutorial, this is part of the question. They gave the mass, spring, and then the damping coefficient. So automatically, the first thing, we have M, we have K. The first thing that you do when you have M and K is you find the natural frequency. It's equal to the square root of K over M. So that's 50,000 newtons divided by 81 kgs. Finding this should give you about 24.8 radians. Okay, now we have the natural frequency. Perfect. Next, we have the natural frequency and we have C. We can find the damping ratio to be C divided by 2M, the natural frequency. This you should know by heart, okay? Like this equation. So 1,000 divided by 2 times 81 times 24.8, and we get about 0.249, okay? Now, it's less than 1, so we know it's underdamped. So we know that it's equal to this. Okay, so we already found damping ratio, we found natural frequency. We have to find the damping natural frequency, the damping frequency, A and B. That's it, okay? First things first, we could find the damping frequency, which is equal to this. Again, this you should know by heart. I don't know if it's in your formula sheet, but it wasn't in mine. So it's just something you have to know by heart. It's literally, I think, in every question. So 24.8 times square root of 1 minus 0.249 squared gives us about 24.02 radians per second. Right? Yeah, that's it. This is radians per second as well. All right, now all that's left is to find A and B. All right, so first things first, there's a 5 centimeter drop, so already that's a hint. We're gonna set, and since over here you see the X arrow going down, we're gonna consider that the initial displacement is 5 centimeters, so 0.05 meters. All right, so X of 0 equals 0.05 equals E. All right, since time is at 0, this is 0, so e to the power of 0, that's just equal to 1. We could ignore that. Sine of 0, that's equal to 0, so just forget that. And cos of 0 is equal to 1. So 0.05 equals A. Perfect. Now the way you find B, well, beyond this point, it's just algebra. The way you find B is usually you just have to pick up the derivative of X, and then you consider that the initial velocity is equal to 0, unless if the problem states otherwise. Usually this, like, literally in all of my problems this worked, okay? Now, deriving all of this is really long and it takes time. So that's why you're going to see sometimes in the problem solutions they use this equation. This. Phi is basically the phase lag. It's like how the system, like when there's a disturbance, how the system lags behind some shit like that, bro. Honestly, I never use this shit because it's too complex. I just brute force it and find the derivative no matter how long it is, okay? So I'm just gonna do this quick. All right, so this is a derivative. Even though it's long, honestly, it's like a foolproof way to solve this problem, okay? So we're considering the initial velocity of 0 because it doesn't say anything about it, so it's safe to assume this, okay? At t equals 0, all the signs of 0, it's equal to 0. So this is 0, that's 0. Okay, so there's this, WNA. E to the power of 0 is just 1, and cos of 0 is just 1. So we just leave this as is. Then over here, same thing. This is equal to 1, that's equal to 1. Plus WDB equals 0. We send this to the other side. You got WDB equals damping ratio WNA, right? So B equals the damping ratio WNA WD. So damping ratio, that was 249 times the natural frequency, 24.8. We found A to be 0.05 divided by the damped frequency, this. And this gives us about 0.0129. So the system's response would be x of t equals E, this 0.05 cos W dt plus 0.0129 sine of W dt. And then if we replace the damp frequency, natural frequency, and damping ratio, you should get this result, 6.1. All right, and that's it. That's all there is. That's all there is to this question. It's like, it's not super simple like your other classes. It's just you have to understand what's happening. Okay, you have to understand that this is your normal equation, your general solution, but you have to make sure that this is below 1. It could be 0 or below 1, because if it's 1 or above 1, you have to use a different equation. Then you have to recognize that this is one of the first things that you have to find, by the way, and this as well. And once you find these two, the rest is literally just algebra. You already have the equation for this. Well, you should know it by heart. And then it's just the initial value problem. You find the derivative, do the derivative, no matter how long it is. Who gives a shit? It's a foolproof way. And then you find the result. And that's it. Super easy.